All right. Welcome, everybody. We'll be getting started here in just a moment. Looks like we're going to be right on time today. All right. Hello, everybody. I'd like to welcome everybody here and thank you all for being here and joining us on this installment of our webinar series focusing on in situ chemistry and electrochemistry in the TEM. My name is Tim Eldred. I'm the product marketing manager here at Protochips, and today we have a speaker who is going to share her work studying oxygen evolution during electrocatalytic water oxidation, both in situ in the TEM and via extended X-ray absorption fine structure studies. So our prior webinars in this series that's been covering catalysts and other considerations and methodologies for nanoscale electrochemistry, they can all be found on our YouTube page, or just feel free to reach out to us with the email that you receive with the webinar. It is our privilege to host this series since Protochips users are some of the most experienced liquid cell TEM researchers in this growing community. Many of them have been using this technique for years, which makes them just excellent mentors to learn from. And our speaker today is no exception to that. So feel free to sign up for as many webinars in the series as you'd like at protochips.com/webinar. We're going to be posting registration links shortly for the continued spring and summer webinars. Couple housekeeping before we get started. Everybody is muted, so please enter any questions you have in the chat box and I will read all of them off at the end during the Q&A. And also please fill out the survey that pops up at the end just so we can, lets us know what content you're interested in for future seminars, and so we can continue bringing you the information that's useful to you. And with that, it is my distinct pleasure to introduce you to ALLA SOLOGUBENKO. She grew up in the Ukraine. She earned her master's in low temperature physics at Kharkov University. Staying in Kharkov, she then earned a PhD in low temperature physics at the Physical Technical Institute of Low Temperatures, focusing on studying the interaction dynamics of magnetic vortices with lattice defects in ultra-pure superconductors. Following that, she changed her research topic to another field, namely the physics of phase transformation in metals and alloys. She completed her second PhD on this at the physics department of ETH Zürich, where she completed a thesis on ferromagnetic shape memory alloys. During that thesis, she really started to use TEM and really came to love the technique. After her doctorate, she went on to complete a postdoc working on her TEM expertise, working on several different research projects, before ultimately returning to Zurich for another postdoc on a number of materials, including metallic glasses and thin films. Her main techniques were TEM, SEM, and FIB, and she is now a senior scientist at SCOPEM, which is the Scientific Center for Optical and Electronic Microscopy at ETH Zurich. There she supervises, supports, and participates in a number of projects, including in situ TEM and in situ LPTEM. And her main expertise fields are microstructure analysis, phase transformations, and analytical studies, including EDS and EELs. And with that, I will hand everything off to ALLA. Take it away.
Hi, everyone. Hi, everyone. I hope you will understand my English. All my colleagues and students do. So let's start. Now, my talk will be about oxygen evolution reaction and catalysts for this oxygen evolution reaction, but a few just motivation slides come at the beginning. The whole story is about producing the green hydrogen, right? A lot of you, I'm sure, know what it is, but just for those who are new to the field, the green hydrogen is a renewable energy source that can be stored, transported, converted, and at any given moment taken to produce electricity and heat. And during this utilization, it emits only vapor, water vapor. So no carbon emission, no carbonation species emission. And how to produce a green hydrogen? The simple way, not trivial, but simple reaction that allows to produce hydrogen is water electrolysis. And the schematics that I took from the reference here just shows you if you run the low current, through the water, that hydrogen evolves at the cathode and oxygen evolves at the anode. The main challenge is produce hydrogen efficiently. This is the whole story, and this is where this term catalyst will come into play. Now, when hydrogen is produced, then it can be converted to electricity and heat by fuel cells. Fuel cells work like similar to batteries, but they don't need recharging, and as long as hydrogen is supplied or available, one can use this fuel cell, for example, to run the motor of the car. Now, this reaction to feed to fuel cell mechanism, working mechanism, is presented on a schematic, and it's a relatively transparent schematic, but still, so hydrogen is fed to the anode electrode and oxygen is to cathode. Then catalyst at the electrode splits hydrogen into electrons and protons, and they take different passes to the second electrode. Electrons go this way, so yellow pass, let's say, and protons go through the membrane where they unite with an oxygen and electrons to produce water. Again, the whole is a problem to have clean hydrogen, and this is where the story starts. Electrochemical water splitting reaction requires theoretically only 1.23 volts, and in practice it's quite high, quite a bit of higher, and therefore catalysts are required. This electrochemical water splitting reaction can be seen as two half-cell reactions, where the hydrogen evolution reaction and oxygen evolution reactions are working, and both require the both develop at the electrodes that emerge in the electrolyte separated by the membrane. Now, usually these reactions run in a strong acidic or basic condition that in turn impose a very hard constraints on the selection of electron material. So the main motivation for a lot of groups to design the catalysts that enhance or promotes kinetic rate of the reaction, especially oxygen evolution reaction, in neutral or mild media. This is where our story starts. So one of the projects I am talking now about is about a catalyst, particular catalyst, copper-based compound as a catalyst for oxygen evolution reaction is studied and presented here at our work. I was lucky to do this project. I'm a physicist, and all my friends, my co-authors in this project are chemists and electrochemists, which is very advantageous because I fully rely on their expertise and they know what I can do, and this combination is perfect and worked. You can judge how it worked after I finish my talk. Now, we work, as I said, on a copper-based compound, and there are quite a few groups already designing this so-called molecular catalysts, and one of this reference number 2, this group developed and tested in neutral medium this so-called complex copper 2 complex. The formula is here, the molecule, simplified formula molecule is shown here, is considered the most effective copper-based catalyst in neutral conditions. Why are we doing this? We want to study this material, the synthesized material, and we wanted to study that just to understand the mechanism of the reaction, because it is very unclear, and a lot of hypotheses, a lot of discussions, the literature, we don't have a common denominator how it happens, and the reason is that this catalyst undergoes complex reaction path, and this affects, of course, the compound stability and activity, and in turn it poses very much difficulty on controlling the reaction and designing or improving and optimizing the reaction. So we just synthesize the same compound and started the complex study by a number of techniques with a particular goal, to pinpoint onset of the reaction, because it is not clear what and at what potential it starts, and if we're lucky, we hope to identify the true catalyst of the reaction, which again is contradictory information, is not known. So a few of techniques I put here on this slide, but we used quite a few other ones. Now, first, this is our results. I am electron microscopist in this work, and this is my main expertise. I will present on extensively on next slides, but before, the work which is done by chemists already got quite a message, which was a necessity for the efficient TEM studies. Now, chronoamperometry and cyclic voltammetry, as well as in situ with electrospectrometry results, indicate that the compound, I call it compound 1 or bold 1 for simplicity because it's a large formula, starts to decompose already after the few minutes after we run the current through the electrolyte containing this compound. So the indication now, if your electrode without in the electrolyte without the compound shows pretty much constant current density, then if we add compound, we have quite a different performance, but current density after a quite good and promising value drops promptly to about then 40 microamps per square centimeter. And the reason is one of hypotheses verified by a lot of other techniques, was that one has a decomposition of the compound with the formation of copper-based film or particles or something on the electrode. Because if electrode after cycling, one puts the electrode, FT electrode, treated at the condition of the copper-based complex, is treated by ETDA, EDTA. I have an abbreviation decoded. I hope I did it in each slide where it's needed. This compound, this acid, is very well known to remove all metallic species, particles, ions from the surface of FTO. And so you see now, if the electrode is cleaned by the compound, that the current density drops. So we have something at the electrode evolving during the reaction. Then now in situ visual electrospectrometry study again confirms that this broad feature that evolves within a minute, within from about 400 to about 600 nanometer wavelengths, also attributed to the cluster formation at the surface of the electrode. I'm sorry, it's my mouse too sensitive. Now, post-reaction study by energy dispersive X-ray spectroscopy in an ICM2, X-ray photoemission spectroscopy XPS, and also electrical impedance spectroscopy confirm that compound starts to decompose right away after reaction started, and confirms also the carbon formation of copper containing species at the electrode surface. With a very strong indication, very consistent, but to know, we went to TEM to verify it, because TEM is, I have to say it, guys, TEM is the best tool, right? That's it. Now I hope it would work. All right, I engage both of them. This is now working electrode platinum. Here we had a glassy carbon working electrode. This is now the anodic scan is phosphide buffer solution. So you see the pretty neutral conditions. When we run the potential up, you see that small nanoparticles appear at the surface of the electrode and on the surface of the electrode. You see they're going. Then, given time, the smallest particle dissolve. Maybe one does not see it from the movies, but you trust me on that. I have more data. And larger particles form. With the progress of the reaction, small particle disappears, they say. Large formed. This is not a part of the movie. What is very essential? This particle formation starts at significantly lower voltage than oxygen evolution reaction potential value. So in our estimation, it's at about 900 millivolts or something like that, very close to that. It's drastically lower than the value. And at a given time, CV cycling like this, resulted in the formation of the thin film of the surface of the electron. So those particles, they grew and they agglomerated. Now, we analyzed these particles. This is now HADF STM micrograph, so high angle annular dark field image. And you see now the dendritic morphology of the large number of particles in the image. And this is post-mortem, so post-reaction now analysis. But first, we just have to look at the electron diffraction data. Now, we have electron diffraction pattern of working electrode. In this case, it's platinum before we run, I'm sorry, before we ran the scan. Then electron diffraction pattern information of the same electron after the reaction shows immediately that we have different phase formations. So we have indexed, of course. The phase was pretty straightforward, and according to this electron diffraction pattern, we have copper oxide phase forming, which was pretty straightforward, plus, of course, platinum. FCC structure of platinum rings are present there. Now, since we have TEM2 with our exposure, post reaction we ran in TEM mode. If you have a question, I can explain why. But of course, analytical studies they require STM. I switched the machine to STM, and we analyzed what we have in addition to diffraction pattern analysis. We made a spectrum image, DS, and confirmed that we have a copper containing and of course large pickup of oxygen signal and copper signal at this so green areas in this image. Right, this is a unit cell of the phase. Right now, we have oxygen evolution reaction studied reproducibly quite a few times, quite a few runs, quite a few days, months, as usually you work to confirm the data, and we conclude that copper-2 compound does undergo decomposition at the very early stages of upon application of potential. Now, relying on a Purbax diagram, we think that copper could not form a stable copper oxide with a high oxidation state, copper 3 or copper 4, because in the neutral solution, this small copper 3, copper 4 oxidation state, particles will reduce to copper oxide. Next, small copper oxide particles are soluble in water, pretty much soluble in water at neutron condition, and This is why they were not detected at, or reported in a publication consistently before. That's why they can be missed. So one has to look closer and then one sees them. The best would be, of course, to know oxidation state of the species. One has to use some other reliable technique, because yields through the whole sandwich of silicon nitrate membranes with a 500 nanometer, when it bulge even thicker, of basically water. It's way too thick. We didn't see anything with yield signal. So now I have here just intermediate summary of our study. It's a complex study. It was a complex study. We have unstable or not stable copper-2 complex that is added to neutral electrolyte, and after the short time we have formation, or we have a decomposition of the compound, and then at a prolonged period these particles, they transform in stable copper oxide. This is our standpoint at that moment, and this is where TEM, in situ electrochemical liquid phase TEM, made a difference. We confirm that it happens in 2 stages because operandi electrochemical X-ray absorption spectroscopy and electrochemical Raman spectroscopy were applied at the different stages of the part, but TEM could follow the whole path. Now, we can, phase analysis of TEM did state convincingly that we have a copper O phase forming and but oxidation state, to check oxidation state and what exactly occurs and where what is the final state of the stable phase that becomes deposit on the electrode. It is not possible by TEM, just due to, because it's just too much of the mass for TEM. We won't have any decent spectroscopy signal by electron energy loss. For that, we have a wonderful other technique, so EXAFS studies, and for that, 2 PhD students, 2 PhD guys, wonderful young motivated guys, they went to Berlin to KMC2 beamline and performed this average oxidation state assessment on the copper side of the compound before reaction and after the reaction. Now, how you read these graphs, how you understand it, it's, if you don't know how to understand EXAFS plots, it's relatively straightforward. So we have now absorption, right? Absorption, and Fourier, we have already said a copper oxidation state of copper foil is taken as a reference. We have our compound 1, and we have a post-catalytic state, post-catalytic phase. They have different oxidation states. Copper oxide phase is taken as a reference in the graph. Now, if you go to the graph B, that Fourier transform fitting of compound 1, Fourier transform fitting of this red curve is presented here, and it gives a few scattering shells, a few features that we can then follow in the Fourier transform fitting of post-catalytic compound. Now, this graph shows exactly what I'm speaking about. So red is the Fourier transform fitting of compound 1, and the blue is the same for post-catalytic compound, and the reference is copper oxide phase. you see then already, looking at this, that the first scattering shell here shifts to the lower values in post-catalytic compound. And it correlates pretty well with copper oxide coordination shell of copper oxide here. Then, next, second scattering shell of compound 1, which is due to this bond, this coordination shell, is basically disappears. And instead, we have a few scattering shells that also fit in quite very well with the values of copper oxide structure. This is now the main message that you can read from this slide. And now it's our summary based on before exhaust and after exhaust studies. Copper-2 compound, known as an outstanding molecular oxygen evolution reaction catalyst, is studied by a number of techniques, and we showed that actual mechanism of oxygen evolution reaction in the presence of this compound is more complex than the solely molecular path. First, we have copper-containing particles forming at the electrode, then they dissolve. At the later stages, copper oxide particles or dendrites form still at a much lower potential than that of the oxygen evolution reaction of the same compound. This we consider the most plausible true catalyst of the reaction. Now, main message that you anyway probably understood already, in situ monitoring of catalytic reactions has to be performed under operation conditions for the understanding of the real, true reaction path. And then it is very important for molecular design solutions. I finished with my message, and I have a few slides on the TEM part, electrochemical TEM part. If you have any questions, I am ready to hear them. Mike.
Hi, I'm back. I'd like to thank our speaker very much for that. Well, if anybody has any questions, please feel free to drop them in the chat. I have a few questions on technical considerations. I'm a microscope jockey at heart. It's what I do. And so talking about what you were working on, you mentioned the considerations between choosing between TEM and scanning TEM and STEM early in your talk. Would you mind going over why you considered both of those and why you said you're using TEM primarily, but STEM for your analytical techniques? If you want to just, if you wouldn't mind covering some of your practical considerations.
All right, very valid question, actually, then very valid question, because STM, scanning transmission electron microscopy, it actually provides everything, but of course, electron diffraction pattern of some decent volume of material. Non-diffraction we can have, but it's still non-diffraction pattern. So STEM would be the first choice. But considering the radiation damage, and we started to do our studies using STM, but we induce so much very locally. Whenever we start with very low dose, we try to reduce our dose as low as possible. Still, we induced immediately radiolysis. We induce unwanted the reactions that we couldn't, of course, interpret as a real one. That's why we had to revert to TM, and we studied and selected the parameter. We find our parameters of illumination, of current, or everything, to be safe, not to induce, not to change pH value of the electrolyte, of the soup where the whole thing is cooking. And then we were sure we are the most close to the natural reaction path. STEM was no go, unfortunately. in this case. We used a 300 kV machine. I think it is there. Right. It's a ground arm, dual ground arm machine. We will use 300 kV machine, which was quite advantageous, of course, for transmitting through the whole this thick sandwich. But maybe it gave us too many electrons in a very small probe. And that's the thing, that was not the way. Believe me, we would go for STEM. No, we didn't manage. We also post-reaction, that we had a stable phase forming. Of course, we switched to STEM and analyzed electron diffraction and EDS and yields. We tried quite a few times, but it just didn't yield it information.
And so you're saying that the particles that were being formed they're stable after formation, or did you experience sort of degradation or growth of those particles through radiolysis?
No, in STEM, yes. In STEM, we immediately saw the nucleation of the particles and their coalescence. And it was, of course, where we used STM, just insider hint if you do electro studies in TEM, and you have a big bulb, gas bulb, blocking the view. You have a, you don't have an image. It's black. I switched to STEM and just very carefully, I don't move the specimen from the corner. I just push this bulb. I mean, I hit locally the thing, you induce a convection, and bulb shifts. It worked quite a few times. It really helped, and it worked.
That's wonderful.
I was surprised, and I just want to share with you. So STEM is useful, but it was a heavy weapon for our study. Once stable copper oxide particles formed, then STEM was doing nothing bad to them.
Okay. That's an interesting technique that I actually hadn't seen, using STEM to move a bubble that forms in the, I mean, but that's one of the things that kind of comes up when you're doing in situ liquid, is how, especially when you're trying to do a gas generating reaction, is how you deal with the gas. So it's really,
you have to do something, otherwise the whole, a lot of hours of preparation is just nothing, right? If you have a bulb. That's the same. So and really helped, not every time, but quite decent way. You just don't shoot in the center, of course, on the image, but good.
I have one more question. If we go back to the movies where you were showing the particle growth and particle breakdown, and that plot of your CV. So you had mentioned that the particles form and then they break down over the course of it, but is that not a fully reversible breakdown because you see some sort of change in your CV over the course of multiple loops?
Right. Okay. The thicker layer forms, and this is what we attribute. We have now then a direction of a stable copper oxide phase form. Okay. This graph below this core, and it's just one of first cycle is presented here. But if we do the CV cycling, we for more and more and more.
Okay. I think we've got time to start I'm going to start hopping into the questions from the panel, since people had some time to put those in. We have our first question. Just going to read them off here. Thanks a lot for a great presentation. Since you're a TEM specialist, I have more of a tech question. Can we use TEM for hydrogen detection? How can we do it, and what are the difficulties?
In TEM hydrogen detection, it's just you have to deduce that if you have a hydrogen evolution, that it is hydrogen. Okay. Because the DS, you cannot detect hydrogen, and yields is no way. It's just too big to. I don't think it's possible. Mass spectroscopy attached to the TEM will give you very good. We have our mass spectrometer in our machine. I didn't use it. It was complicated enough experiment. So mass spectrometer, of course, can give you the quite decent hydrogen indication of hydrogen evolution. But this is not one of my major techniques, so I would rely on some professional in that.
Okay. I have a, oh, he left without the question. We have the next question. Interesting talk, thanks a lot. Short question, apart from the radiolysis effect already described. Any idea why the copper oxide would grow at those specific places on the electrode surface? Could this be due to an epitaxial effect or specific active sites on the electrode surface, or do you have sort of another theory for this?
You're actually asking a quite valid physical question of the nucleation or precipitation. The thing is, that's why I included two different electrodes. This is platinum, so it's a crystalline electrode, and this was glassy carbon electrode, so it was amorphous. This is now very, very difficult to make to find it in a view without an aperture. Mm-hmm. You wouldn't without objective aperture, which limits the field. You cannot even image it before the reaction started. Immediately, then nanoparticles form at the surface of the electrode, and you see them. You can perceive them already here. And amorphous material doesn't have so much of. You cannot speak about any epitaxy of course, amorphous material. And copper, polycrystalline copper. It's not single crystallite copper. I wouldn't expect any match of copper or copper oxide to the platinum crystalline facets because it's just quite different lattice parameters for those species. I work a lot with, of course, FCC is the easiest way. You know all the orientation and everything. Copper oxide has a more complex structure, but you know the lattice parameters. There is no possibility for the epitaxial match. My interpretation would be you have some non-smooth surface. So you just have segments of, I don't know, grain bonders, the electrode in case if you have a monocrystalline electrode, so it was a printed electrode. And if you have a glassy carbon, it's still heterogeneous nucleation, maybe on some, again, non-smooth or a driving force for the precipitation, some interface is too high, not to start precipitation.
Okay.
So I don't give actually the decent answer, I believe, but it's a very good question.
Yeah, it's a question that possibly could, you know, spawn somebody else's research to look into it. Next question we have. They would like to know exactly what went wrong with the stem eels in analyzing the copper oxide phase.
It was not enough signal to see. It was very, 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 very noisy. You have a basically a beaker of water, and you shoot through, and a small volume fraction of copper or whatever copper species evolve. It just you have to illumination exposure for the yield spectrum to give a decent. Some feature had to be so long and so strong, and I don't even. We tried a few times for I don't know, for 10 minutes or 15 minutes. You irradiate the area, and you hardly see anything. Just too thick, too big, huge volume and to reach the spectrometer. Just if we already consider to acquire, of course, from prototypes as thin spacers, we use 500 nanometer spacer on the bottom chip, but we still went for the larger spacer again to approach the more or less reality. Because if you talk to any chemist, and they have become immediately as a skepticism in yes, what you see then a nanoscale and in our milliliter volume in the beaker and the chemistry lab, it's quite different stories. So you cannot transfer knowledge gained by in situ TEM to the chemistry lab, and that's why we just want to have a larger volume to eliminate, of course, the membrane surfaces that can also become ionized in this electron shower, and they also impose certain constraints on the whole electrochemistry stuff. So we went for larger spacer, but disadvantage was very, very, very low signal for yields.
Okay. We have a question on the synchrotron experiments asking, for the synchrotron experiments, were they done with the samples still on the protochips holder?
No, it was of course not, no.
Okay.
The specimen was post-catalytic specimen from offline work. It was ex situ reaction, and they analyzed it there.
Okay.
It was not TEM specimen, not literally the same material, but it fits pretty well, I have to say. So what one phase analysis, straightforward phase analysis fits so well with the structure that EXAFS reviews. It's good.
So we have two questions that are on sort of the same subject on discussing the reference electrode that you were using for the liquid cell TEM. Talking about using a pseudo-reference platinum or if there were any other problems with the reference electrode. Okay.
But what's the question?
So the first question was just, were you using the pseudo-reference electrode platinum? And then the other was, do you have any problems using this kind of reference electrode? And if so, how do you sort of compensate for those?
Experimentally, it was really for, if I use platinum, it's really very, of course, it's easy to mount. If you mount, you assemble the cell and you look at the binocular, and you have to align two windows. You know, I have the schematic here.
Yeah.
You have to, it's here somewhere. Right. You have to align, you have two chips, bottom chips and a top chip, and top chip has the very narrow, slim, narrow window. You have to align it over the window in the bottom chip, and inside of this window there is an electrode. You can perceive it, you see it in the binocular, and you have to align those things without fracturing the silicon nitride membrane. So platinum I could see, glassy electrode, glassy carbon electrode I couldn't see in the binocular, so I related when I assembled the thing, the whole sandwich under the binocular. It was really just a size of the window. It's just experience probably. If you do it X times, X plus 1, you already have this hint. So platinum was easy from this point of view, and of course from the contrast immediately in TEM. For glassy carbon I looked for, I don't know, for a few minutes, and even with an aperture to find it, and then you have to be fast, because once you focus or condense the beam to make a higher contrast or something, you're always afraid to induce already some changes, right? And you don't need much of energy to start it, to initiate that. But in STEM, it would be wonderful. STM HADF contrast, it's very much more sensitive. Mass thickness contrast of STM is much help, but we learn pretty fast, we cannot use it.
And from sort of a
just practical point of view, but I'm not sure that was the question. Maybe you mean something chemical side.
From an E-chem perspective, did you have any issues in selecting between your reference electrodes or
not really. We just recalibrated them relative to the standard chlor, standard, I mean, silver chlor electrode material. We just calibrated them before we ran our barometric scans on CV runs, and that worked pretty reliable and reproducible. Not really. It was actually expertise of Ismail, the guy. We worked as a electrochemistry in TEM. It's a 2-person job, as I see it. This is Ismail. He is now starting this controller, and I was a TEM driver, or whatever how we call it. And this is now was his expertise, and he never had any issues with some calibration or shifts or no. Never heard him anything mentioned about that.
We have one more question in the chat here. Have you compared the OER activity of a deposited sort of pure copper oxide film for comparison? So if this catalyst decomposes to a pure, not mixed copper to oxide film, then it should have a similar electrochemical response to an intentionally designed copper oxide film?
In our experiment in situ TEM, we didn't do a copper oxide. It's just to elaborate, it's a X hours for doing reproducibly this, but I understand it could be done. Didn't do it, I have to say. But in situ, other in situ electrochemical measurements in the chemistry lab were done using also copper oxide as not a reference but a frame of reference. Sorry, I went too far. So in these measurements, the copper oxide material was included, and we also had a copper nitride material as a frame of reference curves. But in TEM we did not. No. It's a good, actually, I don't know what we would see, but it would. It's a wishful thinking, right? If you had enough time, if you have enough chips, enough, and so on and so on. But it's a very valid question. What I don't know what you expect from electrochemical in situ liquid phase TEM on a copper oxide, but it would be very nice reference curve. You're right.
All right. We have gotten through the questions that we have there. I'm going to give everybody just a minute or two more to submit any others. Are there any sort of practical advice you would give somebody who's looking to, either electrochemists looking to add TEM to their repertoire as an additional characterization method, or microscopists who are potentially looking at liquid cell projects, potentially coupling it with electrochemistry? Sort of, you've been doing a lot of work sort of uniting those two, working with Esmail. Do you have any advice to people on sort of both sides of the aisle?
I don't know, it's just kind of half a joke advice. It doesn't matter when you start your experiment, the real data starts to come after 6 o'clock in the evening. So just be prepared, and whatever, you can spend 8 hours of assembling and reassembling and doing and trying, but so actually it requires endurance, but it's doable, and it makes it's fun. If you have the beautiful data and you have chemists working with you, it's just in tandem. It makes it really fun to have as a physicist, chemist, electrochemist with you. So this is probably general and serious advice. Have a specialist on the technique. We have a combination of technique, and we put those big techniques in one experiment. Have a profi beside you. It's just always, it's nothing new to everyone. Otherwise, no. Once you're new to the field, you just start. It takes a lot of time, but you had a bump on your head and you avoid the turns. That's it.
I appreciate it. I think that is all of the questions we have today. So thank you again so much for the talk. We had and the great discussion that we had going on here. Thank you so much for your time, and everybody have a wonderful day.
Maybe use Mike, you can say Tim, sorry Mike. Tim, yes. You can suggest to the guys that if you have any questions coming later or so, you have my mail. You just write my mail. Well, next week I will be in Darmstadt. So if you accidentally there at the MC conference, you just find me. I'm in a program, and you know my face, I hope now. Just come to me. If I can help, then I can. If not, okay, I will learn something from your questions. Thank you very much, and thank you, Protochip. It was
thank you so much for your time.
Working with you today too. See you all someday. Bye bye.
Goodbye.
Bye. Oh, okay.